All right, hi everyone. Billy, make sure you speak to someone, probably Catherine, or me about generating the parent function for f of x equals sine x, okay? Also, I'm going to be referring to my two TFA sections here. One of them is the section with Jace. Section with Jace, the beginning part of this is the vocabulary that I had not covered with my section with Asher, or I should say AKA the most handsome of all the grandchildren. I have to say that was just the cutest stinking thing I've ever heard. Asher's grandma said, Asher is our most handsome grandchild, and it was just so stinking cute. Okay, so we had a new friend invited into our family of functions, okay? We have our parent sine function. And Asher's section, you know that the parent sine function, what you did here on this graph paper, and you're going to want to pull out that paper that I gave to you in class, Asher's section. Jace's section, CJ's section, I have a attachment. Print that out, please, okay, and then work on here. What I want to do right here on this first graph is I want to go ahead and graph the parent function y equals sine x, okay, or f of x equals sine x. And you're going to do a couple of things. Asher section, you'd graph this with Mr. Logue, and what you probably did was you just kind of plugged and chugged and said, okay, y equals sine x, let's see, when x equals 0, sine of 0 is 0. When x equals pi over 2 radians, sine equals 1. See how there's 1, and what's nice here is that he put here, this is radical 3 over 2, and here's radical 2 over 2. Okay, and then when x equals pi over 4, look what I'm doing. I'm eyeballing it. If this is pi over 2, here's pi over 4. Sine of pi over 4 is radical 2 over 2. Okay, and this is what we did in class, Jace's section. We kind of graphed this, right? 3 pi over 2. Sine of 3 pi over 2 is negative 1. Sine of 2 pi is 0. This is pi. This is 3 pi over 2. This is, oh my, 5 pi over 4, negative radical 2 right over here. This is, here we go, okay? And this is what Asher's section did with Mr. Logue, Jace and CJ and Catherine and Ria's section did with Miss Yam today. We graphed the sine function, and what we did first is we looked at angles from 0 to 2 pi, okay? And then what we did was I said, well, let's just finish the rest of this, and what we found here is that this curve, okay, this curve is, so we're going to do some vocabulary word, and here's where Jace's section, okay, Jace's section, we did this today in class. This curve, the curve, which is y equals sine x, okay, is a repeating. It repeats itself. This pattern repeats forever and forever because we can go round and round in the circle, right? We could look at coterminal angles. I should also say this, at 30 degrees, which is pi over 6, where would that be? Well, if this is 90 degrees, and here is 45 degrees, right? 30 degrees is right about here, and sine of 30 is a half. It's pretty good, right? Sine 30. Similarly, if this is 90 degrees and this is 45, 60 degrees is about here, and sine of 60 is radical 3 over 2. So I love that Mr. Logue had made this graph paper with these points, like saying, here is radical 3 over 2, here's radical 2 over 2. How thoughtful, Mr. Logue. How wonderful. This is where I'm going to go into some vocabulary, Jace and CJ and Billy and column section. Asher section. What we have here is a function that is cyclical. It is repetitive, okay? A function that's repetitive, and by repetitive I mean if I took my pen and I wanted to keep graphing it forever, right? It's a cyclical function. I'm going to go over here and say y equals sine x is a cyclical function. It's a cyclical function. Is a cyclical, repetitive, right? Periodic, sinusoidal function. Of these four adjectives, the word periodic and sinusoidal are what I want you to remember. What does periodic mean? Periodic means repetitive, cyclical. Sinusoidal, okay, this is new for you, Jace, too. Sinusoidal, yes, you can think of it as repetitive and cyclical, but sinusoidal, if I'm going to really flesh it out, really means wave-like in a repetitive fashion. Wave-like and repetitive in a repetitive fashion. And I hope the wave-like is obvious, right? It's like a wave, right? So y equals sine x is our first periodic function, is our first sinusoidal function. Every function has unique body parts. You know, exponential functions have the unique body part that they have horizontal asymptotes. Logarithmic functions has the unique body part that it has a vertical asymptote. Y equals sine x also has unique body parts. Let me share with you what they are. There is a horizontal line that cuts the wave in half, so to speak. Here, for the parent function, this horizontal line right here, what's that horizontal line, everyone? Yes, it's the line y equals 0. And that looks ridiculous. Y equals 0. Y equals 0 is called the axis of the wave. Okay? Axis of the wave. What is the axis of the wave? The axis of the wave is the horizontal line that cuts the wave in half, so to speak. Okay? The distance from the axis of the wave to a high point, and that always should equal the distance from the axis of the wave to the low point, is called the amplitude. This distance here is called the amplitude of this sinusoidal function. And what does the amplitude equal here? What is this distance? Yes, the amplitude for the parent sine function equals 1. That's the amplitude. Okay? And then finally, there's something called the period of the function. The period, okay, the period of y equals sine x, okay, let me write it out first, is the horizontal distance over which one complete cycle is obtained. Okay, keywords here. When we're talking about the period of a function, the period of the function is the horizontal distance over which one complete cycle of this endlessly repeating cyclic curve is obtained. And ladies and gentlemen, that period is 2 pi, because I'm going to scan right here. Look at the distance from x equals 0 to x equals 2 pi. Do you see that over the interval from x equals 0 to x equals 2 pi, one complete cycle is made? That's why 2 pi is called the period. So here, the period, y equals sine x, oh my goodness, y equals sine x, has a period equal to 2 pi. And I'm going to go over here and do something. Okay, Jace and Ria section, tune in. I'm going to go over to my parent sine function, and I'm going to highlight that portion of the y equals sine x graph that is traced out over one period. Okay, if I said to trace out the portion of the function that would be graphed over 2 periods, you may trace it out like this. Or maybe you may trace out 2 periods like this. You may go all the way out to 4 pi, for example. But I want to trace out 1 period. The reason why I trace that out is because this image you see in pink is going to become your best friend. When you're at a party and someone says, what does the graph of y equals sine x look like? You will make this motion with your finger. You'll say, oh, it looks like this. You'll go middle, up, middle, down, middle. All right? What's really important is you're not saying that the y equals sine x function just looks like this. You're saying that this is one cycle that repeats forever. And you're tracing out that cycle that begins at 0. Okay? Let me say that again. Don't do this, but watch me. I could have easily traced out one cycle this way. Right? If I started at negative pi over 2 and I ended at 3 pi over 2, this horizontal distance here is still 2 pi, right? I mean, this is absolutely true. It is one cycle. But I wanted to figure out and trace out that cycle, that one cycle that started at the origin. And you're probably wondering why I am yammering on and on and on about this fact. And there's one reason only. This thinking about y equals sine x and tracing in the air like this is going to make your life much easier when I move forward, which I'm going to do right now. Now we are at the point where it's new to all of you. So graph 1 we've got here, f of x equals sine x. This is my parent function. Don't have the blue here. I wonder if I can undo that. Let me see. Hold on one second. Here we go. We have all the vocab down. We have a new descriptor for functions, periodic, sinusoidal, axis of the wave, the period, and what we've highlighted here is one period or one cycle. This is one cycle or one period of this indefinitely forever repeating function, okay? This is the graph here of f of x equals sine x, the parent function. Come on down to graph number 2. All right, over here I'd like us to do the following. I would like us to go here and graph the following. Let's sketch, okay? I want us to sketch, let's say I want to sketch 2 full periods of g of x equals 1/2 x. Oh my gosh, that's just downright offensive. 1/2 times sine x. Now, here's the question I want to ask you. When you look at this function and you compare it with the parent function, which is f of x equals sine x, tell me what role this plays. What role does the 1/2 play? Well, let's see. You can see that g of x equals 1/2 sine x. I'm going to use function notation here to relate g and f. G of x then equals 1/2 times f of x, correct? And what do we know this number does? If we have a number that you multiply by a parent function, what role does that play? Yes, you are right. This number multiplies, what does it do, everyone? It multiplies every y coordinate by 1/2, right? But everything else stays the same. So what I'm going to ask you to do over here on this axis, you're going to pause me now, is do two things. In a light pencil, go ahead and graph the parent y equals sine x function, y equals sine x, and then go ahead and graph g of x, 1/2 sine x, and then replay me, please. Thank you. All right, look what you've got, right? Here is 1/2 sine x. What do you notice the 1/2 did? If 1/2 multiplied all the y coordinates by 1/2, what this 1/2 did was it affected the curve's amplitude. So I'm going to make a jump here and say that this 1/2, right, when we have 1/2 times sine x, the number we multiply by sine x becomes the new amplitude. Because if you look here, this distance now, right here, the distance from the max, the high point, to the axis of the wave, and the distance from the axis of the wave to the min, or the low point, is equal to 1/2. All right? Okay, now you're going to do something with me. Watch, watch, watch. All right? One of the things that's really fascinating about y equals sine x and sinusoidal functions in general is when people learn how to graph these, you can go the really long route where you kind of sit there and you plug and chug each individual point, or you can kind of start using, well, I guess your brain, right? And think to yourself, is there a pattern that I could observe that would help make graphing more efficient? Well, let me show you. Come down to the third graph. Okay, this one we're going to do together. Let's say I wanted you to graph this curve. I want you to graph y equals 3 sine x. Okay? y equals 3 sine x. Well, you already know that this number 3 is going to multiply all the y coordinates by 3, which means then this number 3, right, if the amplitude or the high point was at 1 in the parent function, correct, you know then the amplitude here is going to be 3. Oops, oh well, oh, hold on a second. Our graph paper doesn't go to 3. Let's make it 2, sorry. Okay, so here you know that the amplitude of this wave is going to be 2. The amplitude of this sinusoidal function, or the amplitude of the curve y equals sine x, is going to equal 2. Okay, and again, the reason why is because the amplitude of the parent function is 1. Now here's where I want you to watch me do something. Ready? We're going to graph this together quickly. At a party, you know the graph of sine x starts in the middle. It starts on the axis of the wave, hits the high point, axis of the wave, low point, axis of the wave. Watch me over here. Ready? Amplitude is 2. Here's the origin. Y equals sine x starts in the middle of the axis of the wave. Okay. At pi over 2, we're going to hit a max, a high point of 2. At pi, we're going to hit a low point. At 3 pi over 2, we're going to hit a low point. I think I just had a speako. I meant at pi, we hit the axis of the wave. And then at 2 pi, we hit the midpoint. And what this allows me to do is, I'm doing a lot in my head. I'm saying to myself, I know this is the axis of the wave. I know I have to complete one full cycle in 2 pi, from 0 to 2 pi. I know sine starts in the middle, a quarter of the way through the period, it goes to the top. Halfway through the period, it's at the middle. 3/4 of the way through, I'm down low. And at the end of the period, I have come back to the axis of the wave. And here, it's just a matter of curve sketching. Come on down. Come on down. And then I'm going to continue this way. Okay, we're going to do this again with one little change. Are you ready? All right? Okay, let's come down here. Let's do this. Next graph. Oh no, am I out of room? Oh goodness, mine graphed, it's all up here. Oh well, that's okay. All right, how about this one? Let's graph this one. Let's go ahead and graph, if you would. Let's go here and graph. Let's sketch y equals, negative 3/2 sine of x. Okay, that's going to be our final. I'm going to ask you to do a preliminary one with me. Come with me. Let's do y equals positive 3/2 sine x first. Okay, y equals positive 3/2 sine x. Once again, we know the amplitude is going to equal 1.5. Okay, we're going to go to my graph here. Nothing has changed other than the amplitude, right? So the period is still the same period as the parent function. So I'm eyeballing 0 to 2 pi. Period is going to be over 0 to 2 pi. My period is 2 pi. Look what I'm doing. Oh, gosh. Goodness gracious. Sorry. Okay. My period is 2 pi. Make a little mark. Make a little mark. Cut the period in half. Pi. Cut the period in half again here into quarters. Okay, so a quarter period, half period, 3/4 period. Sine x, what does sine x do? Sine x does this. It starts in the middle, quarter of the way through, it hits a high point. Look at my high point, 3/2. Halfway through, I'm at the middle. 3/4 of the way through, I'm at a low point. All the way at the end of the period, at the end, I'm in the middle. Here is my graph of y equals 3/2 sine x. Okay? I'm not going to fill in the rest of the picture until I have my final. Let's go here now. What's going on from y equals 3/2 sine x to y equals negative 3/2 sine x? Yes, what does this negative do? The negative does what? It reflects this whole thing over the x-axis. Reflects over the x-axis. So at the end of the day, my function, my finished product will look like this. Well, this is still on the x-axis. Positive 3/2, pi over 2, positive 3/2 becomes pi over 2, negative 3/2. Still on the axis of the wave, here and here. Now what I've got is boom, 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 boom. Now I'm going to finish the job. Let's see. Pi over 2, negative 3/2, negative pi over 2, positive 3/2, right? We're just kind of filling in the picture. Okay, and here's what I've got. There we go. And of course I'm going to make sure the reader knows that I know it's just going to go on forever. Okay, so in general, the takeaway here is the following. It is, you know that, here's the big takeaway, if f of x, or let's do this, okay, given y equals some number a times sine x, okay, where a could be negative 3/2, you know, a could be, what was a down here? A was 1/2, a was 2, okay? Given y equals a sine x, let's say, the absolute value of a equals the what of the wave? Yes, it equals the amplitude. And why do I say absolute value? Because here, you would never say the amplitude is negative 3/2. The amplitude is definitely still 1.5, 3/2, right? And we'll make a note that if there's a negative, okay, if a equals a negative number, comma, the negative serves what purpose? The negative just reflects the wave over the x-axis. So to take away, the only transformation that we are learning tonight, the only transformation, the only change to the parent sine function that we are playing with tonight is changes in the amplitude and or reflections over the x-axis. Okay? Your homework is the following. Okay, there's your homework, everyone. You're going to need to do one of two things. You'll have to make more copies of this blank graph paper, which is attached. I know Asher's section, you have this, but if you want more blanks, you can print it out. Jace's section, you have to print it out anyway, so you can always make more copies, okay? This is homework tonight, and I will see you tomorrow. Goodbye. Oh, hold on. These 4 don't require graphing. You'll see what those 4 mean. These 4 can be done on regular notebook paper. I think these 2 you have to graph. Okay? All right, goodbye.